Good day, everyone. In this module, we will be analyzing how heat is being transferred through flows inside a closed fluid conduit. At the end of this module, it is expected that you should be able to explain how the velocity profile of a fluid flow develops in a closed fluid conduit and how this affects the average fluid velocity. Explain how the temperature profile of a fluid flow develops in a closed fluid conduit and how this affects the average fluid temperature. Explain how the rate of convective heat transfer differs in developing and fully developed flow regions. Analyze how convection heat transfer occurs in internal flows when the surface of the fluid conduit is maintained under isothermal or isoflux conditions, and compute for the rate of heat transfer in internal flows based on the prevailing flow regime. Let's start our discussion with determining the average flow velocity in internal flows. We have already discussed that the Nusselt number is largely dependent on the flow regime. Therefore, it is a function of the Reynolds number. But we all know that the Reynolds number is a function of the flow velocity. Therefore, in the evaluation of the Nusselt number for internal flows, we must ask what should be the value of the flow velocity that we must use in computing for the Reynolds number. To answer this, let's consider a fluid that is going to flow inside a pipe. Before entering the pipe, it has a uniform velocity of v sub upstream. Now once it enters the pipe, the fluid particles near the pipe wall will slow down due to the no-slip condition at the pipe surface. As you can see, as a fluid particle gets farther from the pipe wall, its velocity starts to increase until it reaches a maximum value at the center of the pipe. But why does this happen? This happens because the fluid particles that are far from the pipe wall must compensate for the motionless fluid particles that are in contact with the pipe wall. But if we think about it, why is there really a need for the velocity of the fluid particles in contact with the pipe wall to be compensated? The primary reason behind this is that mass should always be conserved at any point within the fluid flow. If the fluid particles near the center of the pipe will not speed up, then what will happen is that the mass flow rate at point 2 will be less than the mass flow rate at the upstream side point 1. And we know that this could not happen. Since we know that the velocity of the fluid particles vary along the radial direction, then we can now go back to our original question. What is the value of the flow velocity that we are going to use in solving for the Reynolds number and the Prandtl number? It has been mathematically proven that by averaging the velocities of the fluid particles in the radial direction, the average flow velocity is simply equal to half the maximum flow velocity v sub max. And this value of the average velocity remains constant all throughout the flow. Now let us discuss how to find the average temperature at a certain point in a fluid flow. We have previously discussed that the Nusselt number is a function of the Prandtl number, and the Prandtl number is just a function of the fluid temperature. Now the question is, what should be the value of the temperature that we are going to use to evaluate the Prandtl number for the entire fluid flow? To answer this, let us again consider a fluid flowing inside a pipe whose surface temperature T sub s is kept constant. The fluid enters the pipe at an inlet temperature of T sub I, and the surface temperature T sub s is assumed to be greater than the inlet temperature. Obviously, the fluid will leave the pipe at a higher temperature denoted by T sub E. Now, what happens to the temperature of the fluid particles once the fluid already flows inside the pipe? Since the pipe is hotter than the fluid, then we can expect that as a fluid particle gets farther from the center of the pipe, its temperature starts to increase. Therefore, the temperature at the center of the pipe is the minimum temperature within the fluid flow. Now the question is, what is the temperature at this portion of the fluid flow? The temperature at this portion of the fluid flow can be averaged to a single value which we can refer to as the mean temperature T sub m. However, unlike average velocity, the mean temperature changes along the flow. Therefore, the mean temperature at point 2 is not equal to the mean temperature at the upstream point 1. Now, since the temperature changes along the flow, then it seems that we still have not resolved the question of what temperature to use in evaluating the Prandtl number. As a final resolution to this problem, the Prandtl number for internal flows is simply a function of the bulk fluid temperature T sub B. The bulk fluid temperature is simply the average of the inlet and exit temperatures of the fluid. In the next video, we will discuss about what happens at the entrance region of internal flows.